I'm also going to be recording this session. How many of you are familiar with linked list and Hashmap? Like, yeah, when I say those words, you kind of know like what it is. Maybe you can't code it right away, but you have like an idea.
Are hash maps the same thing as hash tables?
Yes, so that's something we're going to cover today too. They are
Okay,
essentially the same thing because the idea is that in the table, you're looking up that set of values, and same thing, like a map, you look up a set of values.
got you. So it's like linear probing, quadratic probing, all that good stuff. Direct hashing.
Yeah, all that stuff.
Got you. Got you.
Okay, I think that we're going to go ahead and get started. And I think a lot more people will trickle in, hopefully, like while we're going. So my name is Armand Ambia.
And my name is Sun.
And today we're going to be going over linked lists and hash maps. And these are two pretty important data structures. You're going to be seeing these a lot, like the more you code for personal projects, the more you do like interview stuff, the more you do industry work as well, because they have very specific uses. And when those uses come up, these are like the best data structures to turn to. The last two sessions, we had like more of those practice problems for people to work on together. Today is a little bit heavier content wise. So what we're going to be doing is trying to get everybody to participate during the session. So each slide, we're going to be asking you guys questions, and we want it to be a little bit more of an open discussion. There aren't going to be like specific problems that we're going to break you out into breakout rooms though. Our hope is that after this session and the next one, we're going to do a session with just problems. And that's going to be like all of you guys can come in, work together, and just solve problems using all the stuff that we've gone over. So with that said, let's go ahead and get started. Okay, so my first question is going to be, what is a linked list? So if anybody, feel free to go ahead and unmute your mic and tell me what you think a linked list is.
So it's pretty much a sequential data structure, right? Where we have nodes, and each node has, I guess, if we're talking about a singular linked list, it would have two components. It would have one component is like the value it stores, and the next component is a pointer to the next node. And it's just it's just a sequence of these nodes and creates a list pretty much.
Yeah, that's definitely good. So like what I want you guys to remember from what he said is he said it's a sequence of nodes. Regardless of what type of linked list you have, that's essentially what it is. You're going to have nodes and they're going to be connected together somehow. And that's like the basic idea of this data structure. So that's actually goes into nodes. So we're going to talk about the doubly linked list here because that's like the more common one that you'll see. And the doubly linked list has three key properties. So we have the value. In this case, I made it an integer, but it could be anything, right? You could have a linked list of linked list if you wanted to. Like the value could be anything. The node pointer next and the node pointer previous are what kind of like turns these nodes into a list of nodes. So this next is going to point to a different linked list node. This previous will point to another linked list node as well. And if we keep looping through, we can use these pointers to get through the entire list. Now, this is C++ notation. I'm assuming that all of you are kind of familiar with C++, but if not, that star right there is a pointer to memory. So this isn't necessarily a whole node, but it's pointing to a node. Does that make sense?
Yes.
Okay. So some questions. How many nodes can be in a linked list? Is there a limit?
I don't think there's a limit.
There isn't a limit, right? It's basically just your memory. But last week when we talked about arrays, or 2 weeks ago, arrays have like kind of a limit, right? To how many things they can store and so on. You have to set the size of the array. With linked lists and things like this, it's very up in the air. You don't have to set it, and that makes it more flexible. Another thing, can we add more properties to a node? So right now I got 3 here. I got value, next, and previous. What do you guys think?
I mean, you
Yeah.
could, right? But like, most likely, these are only 3 properties you can see, I believe, right?
Depends, right? So the point is that this is the simplest form of a node that you can make, but a linked list, you can add a lot of different stuff. And one of the biggest implementations that's like important right now, have you guys heard of blockchain? You might have heard of like what the word is, but like not too familiar with it, right?
Yeah. So
So
pretty much like a ledger, right? For
yeah, so
crypto and stuff.
blockchain is a linked list of hash pointers. So you have all those hash like values and all that stuff in each node. So it's like a cool implementation of this. But yeah, the point is that you can add a lot more stuff. We're gonna stick to value, next, and previous for like just understanding linked lists. Okay, and the last 2 questions. What's the previous of the first node? So if you have the very first node, what does my previous point to?
Doesn't it point to null?
Null, right? Null pointer, null. It's basically saying like my previous doesn't exist. And that's important because if you don't set these to null, then you won't know when to stop traversing. There are types of linked lists that if you've taken 131, you might have learned about, say, like circularly linked lists or stuff like that that connect together, and then you won't have null, but those are a different case. So what I really want you guys to understand about linked lists is that each node does not necessarily need to be near another node. So what that means is this is non-contiguous memory, and that's the biggest advantage of a linked list. Does anybody know what non-contiguous means? So if we have an array, right? Let's say my array is going to have 10 values. So I'm just going to draw over this. Actually, I won't draw over this. I'll go to the next slide. So let's compare these two. With this array and with this linked list, essentially these have the same values, right? We have 3, 4, 7, and 1 in both a vector and a linked list. The difference between these two is that the vector, all 4 data points, all 4 spaces in memory are stuck together. They're in one block. So you have to find a free block that can hold 4 integers. That is called contiguous memory. It's stuck together. Linked lists are different because the 3, the 4, the 7, and the 1 could be in random places. 3 could be on the stack at the beginning. 4 could be in the heap somewhere. 7 could be in a network server somewhere. Like it doesn't matter. It's just pointers to different places in memory. And what that means is, do I need to have 4 integers worth of space in one spot to use a linked list?
No.
No, right? You could have 1 integer in different places. So that's really important because sometimes our memory isn't that efficient. It doesn't store it that well for us. And so when we have a linked list, we don't have to worry about exactly where we're getting values from, but it'll still keep track of where they are. With arrays and vectors, you have to make sure that memory is free before you can put stuff there. Now, there are going to be advantages and disadvantages to both of those. So for example, how fast can you access a node? So if I told you to get to the node 7, can you do it instantly or not? How would you get this node right here, number 7?
You would have to iterate through the list.
Iterate through it, right? And so that's basically going to be maximum worst case time complexity of what?
Oh, then?
O of n, right?
N.
Linear time, right? So that's kind of like, it's kind of slow, right? We don't want to have to do O of n time every time we want an element, but that's the cost benefit, right? Like you get the benefit of non-contiguous memory. The cost is you don't have indexes anymore. You don't have like nice little indexes that can give you the value. Whereas in a vector, how would you get this number 7? What are the indexes? 0, 1,
2.
2, right? All you have to do is do vector at 7, or vector at 2, sorry, and you'll get that value, right? So it's O of 1 time. It's faster. However, the trade-off was the memory. So I want you guys to start thinking about those trade-offs and the benefits between data structures. That's a really, really common question that they'll ask you on interviews. When would you use a linked list versus an array? And you want to give both sides because that really shows that you know what you're talking about. So the next thing I want to show you guys is a very common problem that I have not seen taught in any 131 class. This is called the linked list cycle problem. If you guys have been on LeetCode before, this is a pretty, like, if you go to the linked list section, this is probably the top question in that section. The idea is you have a head pointer here and you have a linked list and you want to find the node where the cycle starts. So for those of you who have taken like 270A or maybe like higher classes, for a cycle in a graph, that means that you have a node connect on itself. Do you guys see what I kind of mean here? Like this is a cycle. So this red node is where the cycle starts. It's where it's repeating on itself. If I iterated through this, I would go head, next, 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 keep going. Do I ever hit null?
No.
No, right? So that's how you could tell if there's a cycle. If you never hit null, that's like the clearest indication that you have a cycle. But the point of the question is, can you find out where this cycle is, right? So I'm going to show you guys the algorithm that like is basically what you kind of have to know if you want to answer this question, but they don't teach it to you. So we're going to show you that. We have a video here. This is like, it's going to cover the hash map. It's going to introduce that algorithm and it's going to cover linked list a little bit. And it's pretty funny. So hopefully you guys can pay attention.
Oh, we can't hear the video.
Oh, you can't hear it? Okay.
Yeah, we can hear it.
All right, I'll start it over and I will start that video. Thank you for letting me know. I was about to play that whole thing. All right. I think I know why. I have to share my full screen or else it doesn't do it. Okay. Are you guys able to see it now?
Yeah, I'm able to
Yeah.
see it.
Can you hear it?
No.
No? Oh, let me try that one more time. Oh, here we go.
Number.
Now?
Given an array nums containing n plus
Okay, sounds
1
good.
integers, where each
Sorry about
integer
that.
is between 1 and n inclusive, prove that at least one duplicate number must exist. Of course, because of the pigeonhole principle. Child's play. Assume that there is only one duplicate number, but it could be repeated more than once. Find the duplicate number. I got it. If the numbers are sorted, then any duplicate numbers will be adjacent in the sorted array. A simple sort and a linear scan will do. As expected, I knew it couldn't be that easy. But if you think that would stop me, then you underestimated me. I have no choice but to use my secret weapon. Hashmap.
That's how I want you guys to be. Hashmap should be your secret weapon.
The famous Hashmap, one of the most powerful data structures for reducing your time complexity, taking advantage of its constant lookup times. However, using a Hashmap requires me to increase my power level, so I need to wear these to suppress and control my powers in case it gets out of control. Also, my doctor told me to wear them to treat my carpal tunnel. Nani? Wait.
So that's like where the problem comes in. It has to be O of one time and O of n squared less than O of n squared complexity. So a lot of what we think to do doesn't really work for finding that linked list cycle.
This question is too strong. I'm too weak. I'm running out of ideas. I can't solve this mean problem. How can I even be a real engineer? How am I gonna get into Google? Seems like you need some help. This question is trivial.
Oh my god, he's so cool. And his jacket is so big.
Solving this in linear time and constant space requires Floyd's tortoise and hare, a simple cycle detection algorithm where one pointer traverses twice as fast as another, and once they meet, you can trace back to the point where the cycle began. In our case, the values of the array is like a pointer, pointing to indices of the array, which is like nodes in our case. Because each number is from 1 to n, then each value will have to point to a valid index, and since there's a duplicate number, there will be a cycle. Find that cycle, and you will have your answer. What are you waiting for? Code it yourself. Senior engineers don't code anymore. Also, my doctor said not to, because of my carpal tunnel.
That works. Senpai, why are you so smart?
Because I'm a gangster.
Okay, so that's kind of like an intro to this algorithm. And so like I want to draw it and show it to you because like this actually helped me a lot. So what they start with is the tortoise and the hare. So have you guys ever heard of that little story, like the tortoise and the hare? Like when you're a kid growing up? Is anybody familiar? It's like where they have a race and then the hare's way faster, but the tortoise ends up winning in the end. It's kind of similar to that. So here's what I mean. So we're gonna have the tortoise and the hare. Okay. So the tortoise is slower, the hare is faster. The hare is so fast that every time he's gonna move 2 steps, and the tortoise is gonna move a single step. Okay. So we're gonna just I'm not gonna write the code for this algorithm, but like you can look it up after this. It's really after you see how it works, it's not too bad. Okay, so we're gonna pretend that we're doing iterations. So we said the tortoise moves 1 step, the hare moves 2 steps. Does everybody see what I just did? They both started ahead and then they started moving.
Yeah.
Where are they gonna go next? It'd probably be easier if I had numbers here, huh? Okay, here. I'll draw 1, 2, 3, 4, 5. I shouldn't have done red, that's my bad, but hopefully you guys can tell that's number 3. Okay, so where's the tortoise gonna go next? And where's the hare gonna go? Remember, tortoise is 1 step, hare is 2 steps.
So
tortoise
tortoise
is
to
gonna-
1. No, go ahead.
The tortoise is gonna move to 2 and the hare is gonna move to 4.
Good. Okay. Now where?
Tortoise to 3, hare to 6.
6. Okay. Now what?
Tortoise to 4, hare to 3.
Good. Now where?
Tortoise to 5, hare to 5.
Bingo. Okay. So now they're at the same spot, right? So what the algorithm does is when they meet, move the tortoise back to the start. So now he's head again. Now you are going to move them both 1 at a time. Okay. So now 1 step for both of them. Okay. Where's tortoise going?
Tortoise to 1, hare to 6.
Right. 1 step. Good. Okay. Next.
Tortoise to 2, hare to 7. And then tortoise to 3, hare to
What the?
tortoise to 3 and then hare to 3.
And that is the answer. That is the node where the cycle starts. So that's a really good algorithm. It's with 2 pointers. It's going to be O of n time, and it's going to be O of 1 auxiliary memory. So you don't have to create any extra memory is what that means. And it's a really good one to keep in your back pocket because when any linked list cycle question, you could probably use this algorithm in some way and get the answer. Okay, so now we're going to move over to hash maps, and Alex is going to take over. And I'm going to clear all these annotations. Okay.
Okay, first question, what is hash table or hash map? Have you guys, learned about it or heard about it before? Feel free to unmute your mics and, let me know. you guys will, heard about the hash table.
Does anybody have an idea what a hash map is or a hash table?
It maps keys to values.
Maps keys to values. That's really good.
That's true. Anything else? Okay, I think we just gonna jump into the definition of hash table. So hash table also hash map. Like some of you have a question before, why is the name different? But I think they're pretty much the same. It a data structure that basically maps keys to values, and a hash table is a hash function, which we're gonna mention it later, to compute an index into an array of bucket or slot from which the corresponding values can be found. And based on the hash table index that we create from the hash function, we can store the value as a average location. And there are three main things of a hash table. The first one is a good hash function to generate the index. The second one is have to be support insert, search, and delete function. And the last one would be a data structure that account for collision of the keys that we're gonna mention later in the section. So we have an example right here, and we have three different cases. The first one is John Smith. Can someone let me know for John Smith keys, which location that go through on the image that point to?
2, right?
Yep. About Lisa.
What about Lisa Smith?
Go to 1.
Oh,
2.
Correct.
Oh, I mean, yeah.
And Sandra D.
14.
14, nice. I think yeah, I got it. Okay. Let's go to second slides. Okay, so as I mentioned at the beginning about the hash function, which is the first thing when it comes to hash table. So for this one, I know the code can be like a little bit complexity, but for this one right here, I'm just using a simple, really simple function that simply sum the ASCII values of the string and mode it with the size of the array. So if you go to the next next slide. Okay. Sorry, give me a second. Okay, sorry. So as you can see, so for example, to demonstrate the hash function, we have like keys and values. So the first one key we have like pulse, right, and value 29. And for example, we have an array of items that have a size 8. So what happened is we want to transfer the key value to ASCII values. So the first one we have the p minus a equal 15. It's like under the ASCII value is equal 15. But however, the arrays of items size only 8. So it's definitely not going to fit the array size. So what we need to do within the module is size of 8, and what we have will be 7. So we know that for the key pole, we can point to the index 7. And same thing with Jane, and for this the ASCII value, we're going to transfer to index 2, and Chloe for index 3, and Alex going to be index 1. Okay, and can you go back to go back. Come on, go back. Okay, so so that the data structure, the first thing, the second one gonna be data structure of a hash table. So definitely gonna be you're gonna need the keys and values of character, and also the class of the structure of hash table itself, which contain an array of pointers that point to them, so you can double check, and also size and count to keep track of the size of a hash table. And go to next slide. So we know that for the hash function, we're using the ASCII values of the key, and we mode it with the size of the array item to return the index. However, what if the two keys share the same values? Like for example, if we have a hell and code COU share the same values, what happened? Collision, yes. And what's going to happen with collision for an array?
Does anybody have an idea of how we handle collisions?
Handle it like multiple ways, right? Like linear probing,
Um,
quadratic probing,
Mhm.
joint hashing.
Yep.
Mhm.
So I think you're familiar with that concept. So we go to next slide. Today I will mention what the common one. So that's the way it's indicated. The name is a separate chaining, which aim to create an independent chain or ordered items that they have the same hash index. So if you look at this example, right, that I point out right here, for example, we have in the past, right, John Smith, and going through the bucket. Oh, by the way, so for the bucket, quick question: how do you get these bucket values again? How can you generate the bucket values?
Use the hash function.
Yes, correct. You got it. So what happened is, for example, right, for the key John Smith, going to the hash function, we generate a values 152 on the bucket, and same thing with standard D. So what happened to because these two share the same bucket values, we using the linked list to link to the same location. So when John Smith get into, for example, if John Smith is the first input, right, it generate going to the bucket values, then generally going to second. Then what happened is it generates a linked list that point to the same location. So Z2, John Smith and Standard 3 still share the same bucket, still share the same location, but they have linked to each other kind of training. That's what I mentioned, to share the same spot together. In here, you can, I will have a video show you guys demonstrate how it's look like. Yeah, that's fine.
Okay, so suppose we have the following hash table, which
It's
is
not
just a
here?
fancy name for an array of key
Yeah, we can
value
hear.
pairs
Okay.
of age and names. And we associate an arbitrary hash value that has been computed with some hash function. So those are our hash values. They don't really matter for now. We're just going to see how we can use separate chaining to handle the collisions. Okay, so on the left is our hash table, so our array. And I'm going to be inserting all of these key value pairs into this hash table via separate chaining, and you'll see how easy it is. Okay, so our first person is Will, his age is 21, and he hashed to 3. So we're going to put him in that slot 3. Leah, age 18, hashed to 4. Since she hashed to 4, we're going to put her at index 4. So the hash is a way to index into the array. Okay, Rick, age 61, hash 2. We're going to put him there. And Ray, age 25, hash 1. Okay, we're starting to get a little bit full in our hash table here, so we might get some collisions pretty soon. Okay, Lara, age 34, hash to 4, but we say, oh shoot, Leah is already there. What do? Well, in separate chaining, we just chain along. So essentially each position in the array is actually a linked list data structure. So we're going to scan through the linked list and see if Lara exists, and if Lara does not exist, then we're going to add Lara at the very end of the chain. Okay. So Ryan also hashed to 1, but then we look and Ryan is not equal to Ray, so we need to add a new entry at position 1.
Okay, I think that's
Lara,
good. So people have a visualize. Now we can try the visualize Algo, so we can see exactly how it's look like.
One thing I do want to point out before we switch is, remember how we talked about linked list not being contiguous memory? So that's a very like big part of why they might do separate chaining instead of doing like probing. So, or sorry, instead of doing, yeah, like linear probing,
Linear
quadratics.
probing.
Yeah,
Mhm.
because with the chaining, this block right here, these four are in contiguous memory, and every single collision results in something being pointed to somewhere else. So I do not need as many blocks of memory like in one big section if I do it in this method. Does everybody kind of see what I mean? Because everything that collides with it is going to be off somewhere else, just it's going to get pointed to. If not, then what would happen is every single value would be mapped inside my array.
And we have a huge chunk of data.
Okay, and so here is a little bit of an algorithm that's, or like a website that can kind of help visualize this stuff. So we're going to create a hash table and we'll make it size 10. So this is an empty hash table now. And we're going to go ahead and just insert a few random values. So if I put in 0, where do you guys think this is going to go?
To 0 index.
Yeah, what about like 8?
Second to last index.
Right, so I'm going to add these 5. Okay, so it's mapping. So far, so good, right? Okay. Now, what happens if I add 11?
Remember the hash function. That definitely can help you with that.
So do you take the modulus of
would
do
go-
11 mod 9 and then
Mm.
go into that index?
Is it going to be mod 9 or mod 10?
Mod 10.
Mod 10,
Oh,
right?
right. Yeah.
Because
yeah,
the size is 10.
The size of the
And so now it starts creating that linked list. So this 11 is up somewhere. Now, bonus, like if I were to do linear probing, where would this 11 have gone?
To 3?
To the 3.
To the 3, right? Why?
Because it's the next empty space.
Right, it's the next empty space. And so when you do it that way, you're going to fill up all the spots faster. But then obviously that'll result in more collisions, right? So again, like everything that you do, there's going to be some trade-offs. Okay.
Yeah, so I put the link on the chat, so you guys definitely can check it out and go play with. So you can see the visual of how the training look like. For the conclusion hash table, so definitely the first one you need to do is use a hash function to find an index, and hash function is definitely the key point of the hash table, and also need to store the key and values pair. And also, like you mentioned before, like collision can be handled like by different algorithms, like linear probing and double hashing. But I think separate chaining is like one of common choices, because we like one benefit definitely can be the space. Other than that, why you might wonder why, like you have to create a hash table, hash map, and have to go through a bunch of like suffering so much thing. But the benefit of the hash table is that it's really fast when it comes to access time. In fact, on average, the time complexity of EF4 is actually over 1. It's a constant time. And worst, I believe, say n, nothing more than that.
Okay, and then one thing I wanted to ask you guys is, so now we've covered hash maps and we have a pretty good idea of how those work, right? We get our keys, we use our hash function to get like the index that it maps to, and then we learned how to handle collisions. So what would be the difference between a hash map and say a regular map? Any ideas? Before we started, someone said that hash maps map keys to values, right? Well, that's also what a regular map does. The only difference is there's no little like hashing in between, right? And so that's really useful too. If you create a map of values, you can just make the index whatever you want. For example, like if you were doing, say, if you were just saying like you had a map of everyone's name and then whatever score they got on a test or something, then you could just use their names as keys and then the values would just be the scores they got. So there's a lot of different like implementations of maps, and hash maps are just one form of those. So just keep that in mind when you're thinking about when you could use this sort of key value idea. So these are some extra resources. I can paste these in the chat, and I'll go ahead and do that after we finish up for today. But what I also want to show you guys is there are these leak code problems. So these are some good leak code problems for linked list and hash maps. I've been asked about 4, maybe 5 of these on interviews before, and they're straight off of leak code. So if like you guys do these problems, you're good with it, you're probably going to be good on those technical portions. I can also paste these in the chat. So that's all we have for today. And now I want to open it up to if you guys have any questions about like the stuff that we covered, because we know those two are pretty dense
heavy.
topic. Anything that we covered that maybe wasn't too clear, maybe you want to go back to?
So are we ever gonna, is there ever gonna come a time when we have to create our own hash functions, or is it always gonna be like the take the value and then modulusify the length of the container?
So that modulus is a very common just to teach you type of hash function, but you would never use that as a hash function because it's very much not secure. Like the whole point of those hash functions is how unique can you make it so that you can use it for stuff like blockchain. That's probably the biggest implementation of hashing. But yeah, there are going to be like labs maybe where you have to make your own. And I would expect that maybe in like the cryptography class or something. I don't expect that on the job they'll make you make your own hash function. If anything, you'll be using regular maps.
Yeah, I would definitely say it depends. Most of the time you can use a built-in library of hash table and hash map, unless the question is asking you to design the the hash map or hash table, then yes, you need to create your own hash function. So one of the lead code question I actually put in the chat asking you to design the hash map is by yourself, and you need to create your hash function. So I think you can definitely using that one to practice if you want to.
Okay, sounds good. Thank you.
Anything else? Okay, well, thank you everyone for coming today. So our next session is going to be in 2 weeks from now, and we're going to be covering stacks and queues. Depending on how much information that is, we might also cover binary trees that day. And then we're hoping the session after that will be all problems. So today we didn't have practice problems to do, but then that session will have like 4 or 5, and it could be any data structure. So we want you guys to have all the tools in your belt, and then you can use whatever you want to use. Okay, good night, everybody. Good luck with midterms, and thank you all for coming.
All right, thanks, guys.
They all drop so fast.
Dude, yeah, I should not do this week, huh?
What?
This week and last week is midterm week.
Yeah, that's true. And I also just think like that was faster than we thought. We could have put a problem in.
It's okay.
Yeah. Okay. Yeah, I guess it's fine.
Man. Yeah, I forgot this week and last week midterm week. Jesus Christ.
Okay. Well, yeah, that's fine. We'll keep that in mind. When we start working on next week's slides, we will add in some practice questions.
Next week, you're gonna do binary as well?
I'm thinking about it. So if we do only stacks and queues, maybe we'll add some more problems. But if I feel like with stacks and queues, they're simple enough to where we can add the trees as the main section.
Okay. I mean, we can do the traversal tree and keep it simple.
Yeah. That's the thing.
Yeah, do 3 different of traversal. I think that should be good for tree.
Okay. All right. That sounds good. I'll see you on, let's do Tuesday, 1 o'clock.
Yeah, for sure.
All right.
All right.
Bye.
Have a good night.
Good night.